Okay, today's lecture is about why the Earth experiences seasons. But before we get into the reasons of why the Earth experiences seasons, let's talk about what isn't the cause of the seasons. One major misconception is that the distance the Earth is to the Sun as it changes throughout the year, and it does change ever so slightly. A misconception is that that's why we have seasons, and that when we're closer to the Sun, it's summertime because we're closer to that heat source, and when we're farther from the Sun, it's winter because we're farther away from the heat source. But that's not actually the case. We're actually about 5 million kilometers closer during January than we are in July. And moreover, while we experience winter, the southern hemisphere experiences summer. And if we're experiencing summer, then the southern hemisphere is experiencing winter. So the distance to the sun has no bearing on what season it actually is. Um, as an analogy, one of the major important things is this concept of the angle of incidence. So looking at these scenarios, which would cause the ice to melt faster? Well, the answer is scenario one. This is because the sun rays are directly overhead and they're concentrated on this small little area of the ice cube. When going from the side, these sun rays will create more of like an oval or elliptical shape, and that energy will be spread out over a larger surface area and it will melt faster or melt slower. It's similar to skipping a rock off the surface of a body of water. If you take a rock and just hold it directly over the water and drop it, all of that potential energy will be absorbed by the water at once. But if you take that same rock and throw it at an angle, the energy gets bounced and skips off the surface and creates kind of this reflecting concept, this reflecting motion to the energy. So one big piece of information that you need to know about why we have seasons is this concept of the angle of incidence, which is the angle at which a ray of sunlight strikes the planet. The strongest sun is when the angle approaches 90, and the weakest sun is when the angle approaches 0. Um, if you'll notice something about the orientation of the globes, they're both kind of oriented in the same way. This North Pole doesn't shift positions and then point towards the sun over here. It's always pointing or slanted to the right in this diagram, and that's also important. Um, that's because of this thing called precession. We have a fixed precession over the short term. Over the long term, it actually does move. It takes about 26,000 years for precession for our tilt to change its orientation. But for our lifetimes and for the immediate lifetimes around us, the Earth doesn't really wobble. It's pretty much fixed towards the North Star, which is Polaris right now. In around 12,000 years, it's going to switch back to Vega, but right now it's pointed towards Polaris. And as a result of that fixed orientation, um, the Earth always is slanted toward the tilt remains the same, but it's always slanted in one direction in the same point in space. Just to define axial tilt, the angle of our planet is tilted is the axial tilt, and ours happens to be at 23.5 degrees, and we're tilted towards the star Polaris. The axial tilts of other planets are interesting. Mercury has a tilt of 0, which means it's straight up and down. Venus has a tilt of almost 180, which means that it's kind of flipped on its axis. And when viewed from above the solar system, it rotates clockwise. Most planets rotate counterclockwise, but Venus rotates clockwise because its orientation, its tilt is so dramatic. Uranus is also an interesting one because its tilt is almost 90 degrees. So if you look over here, this one, the planet is almost sideways as it revolves around the sun. Um, let's see. So I don't know if this is picking up on the video recorder that I'm using, but here you can see that this video is fixed at Polaris, and really the sky is stationary, and it's the Earth that's rotating underneath it throughout the day. Over a long time, basically what you would see is if you were at the sun, this is what it would look like. You would have direct sunlight during some times of the year, and at other times of the year, the northern hemisphere would receive direct sunlight, and sometimes it would be the southern hemisphere. So basically, the sun is making a direct, it's hitting the Earth's surface at 90 degrees at different parts of the year, and that's what this would kind of look like. All right, let's define a few other terms. Revolution. This is when one body orbits another. A completed revolution is equal to one period, which is equal to 1 year. The ecliptic is the path the Earth follows during its revolution around the Sun, and it's shown in yellow here. The Earth revolves counterclockwise to the Sun. In what ways can the revolution of another planet be different from another? So if you compare these revolutions, some revolutions and orbits are larger, and some are more elliptical. So the orbital size and the orbital shape makes an impact on the on the revolution, on the actual seasons. These are different orbital sizes, and they have it makes an impact on how long it takes for that planet to get around the sun. So Mercury orbits the sun in about 88 Earth days. Venus does it in about 225 days. The Earth obviously orbits the sun in 365 days. Some of the bigger ones are things like Neptune, which takes about 165 years, and Pluto takes about 250 years to get around the sun. Another interesting thing about orbital shapes is their eccentricity. So a circular orbit would have an eccentricity of 0.0, and a very elliptic orbit, a very oval-shaped orbit, would be upwards near 1. The closer the eccentricity is to 1, the more elliptic the orbit. Ours happens to be it's very, very small. I'll show you on the next slide. Ours is about 0.01. So we do have somewhat of an ellipse, somewhat of an oval, but it's really not that bad. Pluto has the most elliptical orbit. It's pretty much like it looks like an egg when viewed from above. Okay, during class you looked at some weather maps. I don't know if this will translate well on the recorder because it's so choppy, but essentially what you should be seeing in these animations is that the pattern of soil moisture and vegetation and air temperature basically just moves up and down the globe, similar to how that first animation showed the globe pivoting back and forth. That's all because the solar radiation changes throughout the year and follows this up and down pattern. And if you compare these two patterns that we looked at, when the Earth kind of pivots up and down, and when the solar radiation goes up and down on top of the planet, neither of these models are correct, even though they're showing what's happening to the Earth. But if you combine them and you take into effect that the Earth revolves around the sun, you get the seasons. And so to summarize, the reasons for the seasons are a result of three things. 1, the Earth is tilted on its axis at 23.5 degrees. 2, that tilt is always oriented towards the same direction, which is Polaris, the star Polaris, we call it the North Star. And 3, the Earth revolves around the sun. These three things in combination cause changes in the angle of sunlight hitting the Earth's surface throughout the year, and that is why we have seasons.